it is a little confusing. Okay, so last time we were together, we were working on writing down some notes and some parallels between translational, net force, acceleration, business, and rotational, same stuff. And I don't know about you, to me, like this was not like the most exciting thing we've ever done, right? But this is really a fundamental piece that I want to make sure you understand, okay? If nothing else, you are probably going to remember that acceleration is dependent on radius and that Alex has something to, get out against Addison. I don't know what's going on there. Addison, you will be glad to know that we did secure this so that this will never happen again. It's not going anywhere. I'm not going to ask Alex to try, but I think it should be okay now. So I think we're okay. But we do remember, hopefully, because that's not going to at least go away from my brain for a little while, that acceleration, angular acceleration, so speeding up or slowing down as you're going around in a circle, is dependent on the torque, right? The torque that's applied. It's also dependent on the mass and the distribution of mass. And you may want to, I don't know if we wrote that phrase before, but you may want to write that down. That distribution of mass is really, really important. Putting those two things together, we get this thing called moment of inertia. It's the worst labeled thing in all of physics that I know of. Like, it's just big and cumbersome, and I'd almost rather that they just made up a new word for it, opposed to, like, it feels hard to say, but that's what it is, and that's what they'll call it. So that's what I guess we should probably call it too, so that we understand and can communicate. And it's marked with the letter I. So we're going to spend today making sure that we really understand what moment of inertia is, and that we can kind of process it, we can internalize it, because, as I keep telling you, right, in AP it's not just about can you plug numbers into an equation. It's really about do you understand how things fit together, right? So that's really what we're going to try and do today. I've got some ranking stuff. I've got some number problems. We're just going to kind of cruise through them. Please ask, and please, please stay engaged. Yesterday when we were doing this, there was one of the problems that we were working on that I thought was just going to be like a quick no problem. We spent tons of time on it because it's really deep. And I want to make sure that you're getting all of that stuff as we go through. Okay? Ask questions. Don't just ignore it, I guess is what I'm trying to say. Questions before we get started? All right. So here's the first problem that I want you to take a look at. I've got a special rod. I don't know why it's special because I guess it's not uniform. It's made of 3 segments of equal lengths with different masses. The total mass is 6m, 6 mass. The question says, will the moment of inertia of the rod be greater about the left end, greater about the right end, or the same in both cases? So I want you to read that and think about it for just a minute. Can you guys see that okay back there? Or do you want me to turn those front lights off? Would that be helpful? Yeah, absolutely. Good morning. All right. So hopefully you've had a moment to process. How's that streak going there, Brian? Go ahead and have a conversation about this. I want you to think about it, talk about it, figure out what the right answer should be. Okay, let me take a look here. What you got? All right, so it looks like everybody said the same thing. Everybody said greater about the right end. You know that just answering the question isn't sufficient for me, though, right? In fact, I don't really care if you got the right answer or the wrong answer. I care if you got it right for the right reasons. Who's going to give me a reason for this one? Go, Ann.
Well, we said, Michael said inertia is m times r squared. Sometimes the m is greater, it would be greater on the right.
So moment of inertia is m times r squared. Everybody's okay with that, right? We're just going to keep that in our brain. And so then say what you just said again, what that little last piece was.
Since n is greater on the right, it would be the moment of inertia would be greater on the right.
M is greater on the right. So the moment of inertia is going to be greater on the right. What?
I just have a question. Would the radiuses be different as well? Because like if you set the point of rotation, if like the point of rotation was like at the end of m, the little m, then the radius would be longer for the section with 3m. But if you set the point of rotation by the 3m, the radius would be longer for the m.
That's what the question is asking. Let's read the question carefully. Will the moment of inertia of the rod be greater, and maybe it's the wording that doesn't make sense here, greater about. So about means that's where your axis of rotation is going to be. So about means where is it going to rotate? It's going to rotate about the left end. So that would be over here. So that's this one. It's going to rotate about the right end. That would be over here. Or the same at both. I mean, that would just be that it doesn't matter. Go.
Well, I just thought of it. I thought of it like a radius of your two wheels down there.
Mm-hmm.
So when you roll the wheel, when the mass, like when you're, for example, when you're 3m is farther out, it moves slower. But when it's closer in, it moves faster. So you want the.
So let's be careful with our wording so that we know what we're talking about. So I think I understand what you're saying, but we're talking about the acceleration, right?
Yeah.
So what's going to be able to accelerate faster or slower, right? Not that it's going to move faster.
Yeah,
Does that make sense? So what are you arguing then?
Well, I didn't even use the equation. I thought of it as the wheels that you were using yesterday on the ramp.
Okay.
When the mass is closer to the center of the wheel,
Mm-hmm.
it accelerates faster.
Mm-hmm. So
And
that means the moment of inertia is...
Greater. Oh, wait.
Let's think about... Whoa, hi.
Greater. It's less of the radius.
Right. Alpha is equal to torque net over I, right? So the bigger that I is, the what for alpha? The smaller alpha is. Is that okay?
Yeah.
So you can certainly think about it like that. The one thing is that you really, it kind of sounds like when you're talking, like you're trying to rotate it about the center, but you're rotating it about one of the ends, right?
Yeah.
Okay. Okay.
Is R from the center of mass or one of the ends?
R is the radius from the axis of rotation to wherever each piece of mass is distributed.
So it's three different like systems, or it's like one big stick that just has different things?
It's one big stick that's made of 3 different materials that are all, glued together or whatever.
So where the center of mass is doesn't matter.
Not really. I mean, that you could look at it like that, I suppose.
Because like, wouldn't the center of mass be somewhere between 2 and 3m?
Probably.
And then that way the radius would be greater if you put it on the left. But if
Yes.
Is that like? I don't know what moment of inertia is. Like I get like the speed is how fast you're moving, but like.
So okay. So let's try, and then Lindy, I'll come right back to you. Is that okay? So moment of inertia is kind of a hard thing to conceptualize. You know what mass is, right?
Yeah.
So the bigger the mass of something, the harder it is to get it to move. Does that make sense? If you have a big box that's really massive, you try and push it, versus a big box that's empty, and you try and move, it's going to be a whole lot easier to move the empty one. Is that okay? So it's the same idea, except that now we're trying to get something to rotate. So one way to think about it would be a merry-go-round. Okay, like on a playground. They still have merry-go-rounds when you guys were little before they took them out because they were too dangerous or whatever. I don't know. So anyway, if you've ever pushed a merry-go-round, okay, so you know that you're trying to get it to accelerate from rest to some speed, right? Angular velocity. It's going to be a whole lot easier to push it if there's nobody on it, right? So you have less mass. Or if you put all of the people right in the middle of it, it's going to be a whole lot easier to rotate that disc. Are you with me there? Is that okay? Than if they're all on the outside.
So is a greater moment of inertia easier?
Harder.
Harder. So
Yes.
higher moment of inertia, more tension in terms of.
It's more difficult to accelerate.
Okay.
Yes. So moment of inertia and mass are kind of analogous ideas. One for rotation, one for linear motion. Is that okay? question, have we?
I'm gonna change my mind. I think it's left because like the baseball bat,
Mm-hmm.
it's harder to swing. It's harder to accelerate if the weight's the end.
Right.
So
Or correct, I should say.
the left.
Yeah.
So Lindy's changing her story to the left end. Does this make sense?
Mm-hmm.
So if we get out this object, okay, and we remember that we can swing and it's going to be much easier to accelerate it if this is where? Really, really close in, right? If you want to take this more like this, I can either swing it like this or try to get accelerate like this, or I can go like this. Which one's going to be easier to get it to accelerate? This one, right? Where the mass is much closer to the axis of rotation. So if I want to talk about ease of motion, because that's what I'm talking about, right? Does that make sense? The easier it is to move, the higher the acceleration. That means, so this is going to be big, that means this is going to be little, right? We want all of this stuff to be close to the axis if we're trying to get it to make it easy. If it's going to be hard, then we want the axis over there. Is that making a little sense? So what is the correct answer for this question? Left. Okay, does that make sense?
We always.
What's wrong?
Brittany
I
had
had
it.
originally said left.
Oh,
And they-
always listen to Brittany is I guess what the moral of that story is. I don't know. Yes. So the answer should be on the left. Everybody okay with this wording here, the about thing? Does that make sense now? If it didn't before? Okay. Okay. Let's try another one. Sound okay?
Mm-hmm.
All right. See if we can redeem ourselves. How many of you have played jacks? Anybody played jacks when you were little, like with the bouncy ball? Okay. Or how many of you are familiar with an XYZ coordinate plane? All right. So we've got a bunch of nerds in here, and maybe children that were a little bit deprived when they were young. So here's the situation. There's a lot of words here, so I'm going to read them to you to help you understand what's going on. 6 small brass and aluminum spheres are connected by 3 stiff, lightweight rods to form rigid objects that are shaped, if you experienced this when you were little, like little jacks. If you're not familiar with that, it's just an XYZ coordinate plane with balls on the ends at equal distances away. Okay? So if that makes more sense to you from your life experience, there you go. Okay? Let's see, the rods are joined at their centers mutually perpendicular and lie along the axis of the coordinate system, XYZ. All the spheres are the same distance from the connection point of the 3 rods at the origin of the coordinate axis. The brass spheres, I'm going to highlight this because it's important. The brass spheres are shaded and they're all identical. The aluminum spheres are identical. They have less mass and are unshaded. For this problem, it says ignore the mass of the connecting rods. The task that you have, the task that I'm asking you to do, is to rank the moment of inertia about the x-axis. Okay? I'm going to give you 30 seconds to take a look at this by yourself, and then I will let you discuss. Does that sound okay? Go. All right. Let me see your boards. All right, we have lots of agreement here. That's awesome. Now, again, as always, Jenny, what am I going to say?
You don't care about the answer, you want the explanation.
I want the explanation. Who's going to give me a good explanation for this one? Otherwise, I'll just call it somebody. Addison, what you got?
So we thought that the only thing that would affect the moment of inertia about the x-axis was the amount of mass that was away from the x-axis.
Okay.
And so the reason we said D would have the greatest moment of inertia is because, wait a minute, it shouldn't be the other way around because it would have more mass away.
I'm just writing down what you guys had written down.
Well, the moment of inertia is right. The acceleration would be the other way around.
Hey.
Right. What is moment of inertia equal to?
Oh yeah.
Mass r squared.
mr squared. So if you're going to find the moment of inertia of something like D, what would you do?
Add up the masses and multiply by radius.
In this case, because they're all equally distributed, right? Yeah. Yeah. So it's going to be, so the total moment of inertia is going to be, in this case, because they're all the same, it's going to be 4 times mr squared. But you don't look convinced anymore. Or something. I don't know. I can't read your brain right now.
Conviction.
No, I am. I forgot that I is different than alpha.
It is different than alpha. That's true.
Yeah.
And this is asking to rank the moment of inertia. So are you okay with that?
Mm-hmm.
Okay, so tell me why B is smaller than D.
B is smaller than D because the aluminum balls are lighter than the brass ones.
Okay.
And
So?
So there would be less mass. And the radii are the same.
So how would I write the total moment of inertia for this one, for B?
Well, first off, are you not counting the masses that are on the x-axis?
Well, I was going to ask that next, so I can ask that right now. Are we going to count the masses on the x-axis?
It depends on how it's
Because
rotated.
then, R would be 0 then. So
Right. So technically, do you need to count them? Yes. But the radius is what? 0? Does that make sense?
How can it be 0 for both of them?
Yeah, that's my question as well.
So this one and this one?
Is it rotating as in like those 4 are like spinning up around like this? Or is
What does it say? Read it.
Oh, wait,
rotating
okay.
about?
Rotating about the x-axis.
Yeah. Okay,
Yes.
that's what I thought.
Yes. So it's rotating around this line. So it's spinning.
The line went crazy.
Whoa, it did. Wow. Let's try that again. Stay. Okay. So it's rotating about that line. Okay? So if I was going to write the total moment of inertia, what would I do?
It'd be...
It'd be like
2m sub b
yeah.
plus 2m sub a.
So 2m sub b. Let's do it one thing at a time. M sub b times r squared, right? So that takes care of that one and that one. What else do we need?
2 times m sub a
Times.
r squared.
And then if we were going to be really good kids, because now we've taken care of that one and that one, if we were going to be completely thorough, then what else would we include there?
M sub B.
2 more, what'd you say?
M sub B.
M sub b,
R
but
squared. For the R is 0, so.
that r is 0, so when you square that, that whole thing goes to 0. Does that make sense? B and C are not the same picture. Why do you think they have the same moment of inertia? Jenny, why did you guys say they have the same moment of inertia?
Because if you think about it, if you took like a picture of the moment of time, but then if you rotated it, C, it would look like B at one moment in time if you rotated like 90 degrees.
Do you see that? These two pictures are based on, like, if we rotate about the x-axis, they have the same moment of inertia, right? Yeah, absolutely. It's just that we're flipping by 90 degrees. And then what about A?
It has the lightest mass.
It has, what'd you say?
The lightest mass.
The lightest mass. I want to do this question one more time just to make sure it's making sense. But instead of rotating around the x-axis, let's rotate around the z-axis. I want you to look at this right now, you and your brain, and then I'll let you discuss in 20 seconds around the z-axis this time.
Sorry, Brittany, we're equal, not no one's greater.
Okay. Brian, what was your conversation back there about? What'd you guys say?
We said that D was the greatest.
D is the greatest?
Yes, and is equal to B.
Oh, okay.
Yeah. Because when it's spinning about the Z axis,
Uh-huh.
they both have the same amount of masses that would be spinning about it. Because like the mass of the actual axis doesn't really matter that much
Correct.
at all.
At all.
So, and then next, and then A and C were equal because they also both have the same amount of mass spinning about that.
Yeah. Does that make sense? So here's the thing. This is what's really important. The moment of inertia changes when you change the axis, right? So it's not just the mass that we care about. It's the mass and the distribution of that mass. Okay? So if you haven't written that down at least 3 times today, you may want to write that down again right now to remind yourself that when you're talking about moment of inertia, when you're talking about rotation, it's the mass that we care about, but also the distribution of that mass. Those 2 things are equally important when talking about moment of inertia. Yeah?
So it'd be different if we're rotating about the x-axis. It'd be different if like one of the z's and one of the y's was brass, and one of the z's and one of the y's was aluminum.
Yes.
Okay.
It would. The way that they drew this, you have lots of nice symmetry, right?
Yeah.
Yeah. But if you don't, then what happens? So like if you had a brass here and a aluminum here, and it's rotating about this, then it's gonna wobble.
Yeah.
Right? It's kind of like, Michelle, can you hop up and grab this when it rolls down? If I put all the mass at one end, okay? So if I set it here, it's probably gonna stay. But if I start it going, let's see if I start it going like here, then it does stuff like that, right? Yeah, yeah. So the things that we're gonna deal with, you don't watch that again because it's right? Because the mass is not evenly distributed throughout, then you get this weird like motion where you've got like acceleration and then D, and then right? And that just gets more complicated. We're not going to play with that, at least not actively in a calculated way. That's why they drew these like this. Yeah.
Okay.
Does that answer the question you're asking?
Yeah.
Okay, cool. All right. So I want to try another problem. This one does actually have numbers in it, so you probably will need a calculator out if you don't have one out already. Let me explain this one really quickly so that you understand. The question says, your friend is creating an abstract art sculpture, or an abstract sculpture. I guess it doesn't say that it's art. We will say that it's art. It is pretty abstract, though. It consists of 3 small, heavy spheres attached by very lightweight 10-centimeter long rods as shown. The spheres have masses of 1 kilogram, 1.5 kilograms, and 1 kilogram respectively. So M2 is the one right down here. That's got the 1.5. The question says, it's 2 questions. What is the object's moment of inertia if it's rotated about the axis here? So that means the axis is here and it's rotating out of the page. Are you with me there? For A, it's rotating like this. And it goes around in a circle. On B, it's the same sculpture, but instead of rotating about an axis like this, it's now rotating about an axis that's going into or out of the page. So it's going to rotate in the plane of the page. See what I'm saying? So the question is, what is the moment of inertia in each of those cases? I'm going to let you can work with each other. That's totally fine. Have a conversation. We'll regroup in a minute. Sound good? Go, go, go. 1.
0.
It's 0, right? So this one for A, that's going to be 0. What's the radius for mass 2?
10 centimeters.
10 centimeters. So 10 centimeters squared is going to be 100 centimeters, right? 100 centimeters times 1.5 kilograms is going to be something like
150 kilograms times.
And we haven't really talked about the units of this thing yet, have we?
No.
It just exists, but we haven't really thought about it. But let's look at it. I equals mr squared. What kind of units is that going to be?
Kilograms times whatever length unit you're using.
Distance, yeah, squared. So in this case, it's going to be centimeters squared. Usually when we do moment of inertia, we'll do it in terms of meters. But as long as you're staying consistent here, it doesn't really matter as long as you're making sense. And then for M3, as it rotates about this axis on A, what is the radius of the circle that this one would sweep out? 10. Does that make sense? Is everybody okay 10 centimeters away from the axis of rotation. So that's going to be 100 kilograms centimeters squared. So something like 250. Look at me multiplying in my head or adding in my head. Yay, team. All right. What about B? Is it the same? No. What is the moment of inertia for the first one the same? Yeah, it's still 0. What about for the second one?
Yeah.
Still the same. Oops, centimeters. And then what about number 3? So Jack, what did you do for number 3? For this mass here.
That one? I
Yeah.
do like Pythagorean theorem and stuff.
For what?
To find r.
This distance here?
Yeah.
Does that make sense to people? So if you spin that thing around, it's going to be further away than a circle for this one, right? It's going to be something like 14 because it's like 10 root 2 or something like that. Does that sound about right?
14.4.
45, 45, 90 triangle, yes? Is this okay? So it's going to be like 1,000 or 100.
99.
199?
Yep.
Cool. Is that okay with everybody? When you square 14, that sounds about right. Yeah.
A squared plus b squared is 200.
Right.
Okay.
Yeah, yeah. I think they just rounded, blah, blah. Yeah, let's call it 200. That sounds about good to me. Either way, this is going to be 350 kilograms centimeters squared. Is that okay? So this is doing the same thing we did with the Jack's problem. It's just actually putting numbers in there. Okay? So all you do is to take each piece and add them up. Yeah?
Okay, I know how to do like Pythagorean theorem, but how do you get the 200? They're at like 14.
Okay, so this distance here
Oh.
is 14, but it's 14 squared because it's r squared, right? Yeah. Does that get you where you need to go? Okay. Questions about this one before we move on? Okay. Here we go. This is the next one. This is the one I mentioned at the beginning that I said, whoa. Yesterday I was like, oh, it's going to be an easy question. Then it was like deep and big and broad. So we'll see how we do with it. Okay, no pressure. I'm excited. I like this question. It has a pulley, and pulleys are fun. Do you all know what a pulley is to start with? It's just a wheel on an axle, usually in, this plane, so that it can rotate and you can help to lift something up or let something fall, right? We played with one when we were doing that Atwood's machine lab way back in the day, okay? When we were dealing with that, when we were dealing with the Atwood's machine, I don't know if you remember, but the pulley was really, really lightweight, had some holes in it even, right? And the reason for that was so that it was nearly massless. Massless compared to everything else that we had in the system. If it's massless, then that means its moment of inertia is 0, and then we don't have to worry about any rotation business. But, my friends, pulleys aren't usually massless. So this question, now we're bringing that whole rotation aspect into a pulley system. Okay? So here's the situation. It says a wheel is composed of 2 pulleys with different radii that are attached to one another so they rotate together. So they're like stuck together. They're going to move together wherever they go. Okay? Each pulley has a string wrapped around it with a weight hanging from it as shown. We've seen those weights before. The pulleys rotate about a horizontal axis in the center. So it's like set up and held there. When the wheel is released, it is found to have an angular acceleration that is directed, and I don't want you to worry about the out-of-the-page business. The thing I want you to know is clockwise, okay? It's directed clockwise. Or counterclockwise, sorry, yes. I wanted to get rid of the out-of-the-page thing. Yes, counterclockwise. Take a look at A, B, and C. I'm going to let you look at these by yourself first, and then I will let you discuss in a minute. Whoa, I want to make that a little bit bigger, but not so big you can't read it. There you go. All right. So take a minute to read and think, and then I'll let you discuss. All right. Let me see your boards.
A
C.
A is greater than B.
Okay, let's have conversations. I like the boards because I like to be able to see kind of where we're at. Let's talk about this. The wheel is released. It's found to have an angular acceleration directed counterclockwise. What was its initial velocity?
0.
0. And its angular acceleration is counterclockwise. So, Zoe, I'm going to put you on the spot because we had this conversation just a minute ago. What did you guys say for A and Y?
Counterclockwise because it's accelerating counterclockwise.
Yeah. If it starts off at rest and it's accelerating counterclockwise, it's going to move in the counterclockwise direction, right? The translational analogous to that would be like the frog. The frog starts off at rest, and if I let him go, is he going to feel an acceleration?
Uh-huh.
Which way?
Towards the earth.
Towards the earth. So which way is he going to move?
Down.
Towards the earth, right? Does that mean that he would always move down if he feels an acceleration down?
No.
No. What's an example of a time when he wouldn't move down even though he feels an acceleration down?
The jetpack. That was pointing upwards.
Right, but not even because a jetpack would imply that there's acceleration upwards, right?
It's out of gas.
The jetpack was going and now is out of gas. So he is moving in which direction? In the upwards direction, right? But his acceleration is in which direction?
Downwards.
Down. Does that make sense? So you may want to write that down. It's the same principle that we talked about before.
It's out of gas.
Okay? So the acceleration and the angular displacement will not always be in the same direction. Oops. But in this case, we know that it will be because of what? What's the key?
It started at rest.
Yes, yes. Here, because omega initial is equal to 0, we know that alpha
Would
and theta will both be the same, which means that it would be counterclockwise. That's the kind of why that we're looking for. That to me says, oh yeah, they actually understand what's going on. Are you with me there? Okay? Not just a lucky hunch. I mean, lucky hunches are nice, but lucky hunches don't prove to me that we really understand. Are we okay with A?
Mm-hmm.
All right. Let's take a look at B. B says, is the direction of the net torque on the pulley clockwise, counterclockwise, or none? Lindy, what did you guys say for this one?
We said counterclockwise.
Okay, and why?
Alpha equals torque net over I.
Alpha equals torque net over I. Okay.
And I is always positive, so if alpha is negative, then torque net is negative.
Does that make sense? That was really good. That's exactly what I would look for in an answer. If you wrote that, perfect. Like, that makes sense. That proves to me that you understand a relationship between alpha and torque, right? It's the same, it's the analogous deal to A is equal to F net over M, right? You know that the net force and the acceleration will always be in the same direction, regardless of where this thing is moving. Okay? Yeah. So because alpha is negative, positive, if we're saying counterclockwise, that means that torque net has to be positive because those are both vectors, right? They both have direction. I doesn't have any direction, so we don't, it's not going to change anything. Life is good? Okay, how are we doing back in the back corner there? Are we happy? This is making sense? All right, next. This is the big one. How do the masses of the two weights compare? Donald says?
We said that the mass that has a...
Can we label these? Since this one's on the little one, let's call it A. Is that okay?
Yeah.
And we'll call this one B, just so we don't have to be like, the one on the left and the one that I get
Yeah.
confused, Okay, go ahead.
So the mass of A would have to be greater than the mass of B. And we said that because, like within TorqueNet, and I mean the B is also sort of somewhat of an explanation. The explanation for B can help with this.
Okay.
Because we know that the acceleration is in the direction of like mass A going down. That's the acceleration of the pulley.
Okay.
And so for that to happen, because A has a smaller radius than mass B, it's similar to like putting the masses on like a meter stick, and a small mass out here is the same thing as a large mass like closer in.
Okay.
And so because A is closer in, A would have to have a much larger mass than B, or at least a larger mass than B to accelerate.
Is that making sense? Yes, that makes sense. I'm going to put it in some words and equations just to make it sit a little bit better. Is that okay? So I really like the way that you were saying that. I'm just going to, like I said, I'm just going to kind of like, so you were talking about torque net, right? Mm-hmm. So we know that the net torque needs to be in what direction? Counterclockwise, in the positive direction. Now, I'm gonna draw this out a little bit longer because I want you to know how to do this and because I know what's coming next and I know that I want you to see this, okay? So what I'd like you to do right now, everybody in your notes, I want you to draw this pulley system and make a free body diagram of the pulley. Okay? I would like you to draw a free body diagram of the pulley. Think this one through and talk to your neighbors. And I'll explain why we're doing this in just a second, but humor me for just a moment here. All right, let's start drawing this thing. Let's see. Esteban, do you have any forces drawn? You say that again? Just on the mat, like, so the mass is pulling on the pulley? Okay. Okay, so like maybe one over here like this. Is that right? Yeah. Okay, and maybe we'll call that the force of mass A. Is that what you called it? Something like that? On the pulley. And then, and did you have another one also?
Yeah.
Of mass B on the pulley also? Okay. Something like this. I keep wanting to write bully, and I don't know why.
The force of the bully.
And I guess, I don't know. All right. Are those the two forces that everybody had? Were there more forces? Yeah.
I had also, because the masses are on ropes, I had the force of the tension against the mass.
So where do you have that force?
On B for sure, but I also have it on A because there's tension on both of them.
Okay. So, friendly reminder, what is a free body diagram?
It's all the forces on blank.
On one thing, right?
Pulley.
What's the one thing in this problem?
Pulley.
The pulley.
Oh, okay, so the rope isn't on. Okay,
So, I mean, you could say the force of the rope on pulley for both of them, but that's basically what I have there. Does that make sense?
yeah, that makes sense.
Okay. Any other forces that you have acting on the pulley system?
I had the ceiling holding it up.
The ceiling holding it up. Where does that one go?
And, well, on the picture there's something holding it, but can it go from
Yeah, so where is that actually applying a force to that system?
at the axis of rotation?
At the axis, right? Yeah, so there's something like an axle or something like that right here pulling up. So we'll call it an axle. Is that okay with everybody? How do you know there has to be a force like that?
Or because then the pulley would be accelerating towards the ground.
Right, and it would have some translational acceleration downwards if the pink ones were the only two things acting, right? And is that happening? I don't think so.
Oh, so then we'd also.
Are there any other forces acting on the pulley?
There would, if there's a force of the axle going up on the pulley, it'd also have to be the force of the gravity on the pulley going down. 'Cause
Right.
You said there wasn't a. Who said this wasn't like massless?
It is not a massless pulley, right? There is mass pulling down, or there is mass of the pulley, so that means that the earth on the pulley. Any other forces that you included in your diagram? Those are the four that I like. Is it important to have all four of those forces on a free body diagram?
Yes.
In fact, it is, yes.
And touching the.
It's true. Now, I was going to write a torque net equation, then I got interrupted by myself and made you write stuff down. The reason that I did that is because I don't know how to write a torque net equation unless I have a free body diagram to look at. You know what I'm saying? A torque net equation comes from all the forces, right? The force times the radius. So let's do this. Here we go. The radius of A times the force of A plus the radius of B times the force of B plus the radius of the axle times the force of the axle plus the radius of the earth times the force of the earth. Is that okay with everybody? This is just like what we did when we were doing bridge problems, isn't it? Free body diagram. I guess I didn't write the F net equation down, but we could certainly do that. What does F net equal in this problem?
Not zero.
Hello? What does F net equal?
0.
But that's
No.
equal 0 because the pulley's not accelerating.
Yeah, F net.
F net equals 0 because there's no what?
Transitional acceleration.
Right, like it's not, the pulley isn't falling down or moving to the left or anything like that, right? So the F net statement equals 0. But does the torque net equal 0?
No.
No, it doesn't, and that's actually really important in this case. I'm going to move this up like this so that I get to move things. Yay. What does torque net equal? Is it 0?
No.
No, because it's what?
Accelerating.
There's angular acceleration, right? Do you remember this one? Alpha equals torque net over I.
Which is also R squared.
So what does torque net equal?
Equals AI. Alpha I.
Thank you. I alpha. Okay? Is everybody okay there? Okay. Are any of those radii 0?
We can make the axle and the earth one 0.
I think that would be a good choice since that's where it is rotating about, right? So let's make those guys 0. And then now we're really getting to the heart of what you were saying before and what I think your gut feeling was telling you. But I want to make sure this makes sense. The torque net is not 0, right? So we know that this is positive. Is FA going to cause positive or negative torque? Positive? And what about FB?
Negative.
Negative. So if we look at this carefully, we have a positive plus a negative has to equal a positive. That means that this product has to be greater than this one. Does that make sense to everybody? Mm-hmm. This product has to be bigger. So if we write that down, so we've got RA, FA must be greater than RB, FB. And this is really what Donald was saying. And if you were answering this question, I don't necessarily need to see all of this, but I want you to see where it comes from. Are you with me here? I want you to see where it comes from. RA is much smaller than RB. So if this product is going to be bigger, what do you know about FA?
Bigger.
It's got to be bigger. Are you with me there? It's got to be bigger than FB. And that's where this comes from. It's a big question. It's a big question. All right.
I have a quick question.
Yeah.
Why is both the radius of the Earth and radius of the axle 0. I understand. I think it is, but I don't know why.
Well, what is R?
Like the radius that it rotates around.
Right. So R is the distance between where the force is applied and the axis of rotation.
And because like it's the force of the Earth and the it's like almost like a normal force.
No.
No. Okay.
No. So to be very clear, it's a good question. These two do not cancel each other out. They do not cancel each other out. Both of those forces are applied at the axis of rotation. This thing rotates about that point.
And is that also the? Okay.
What did you say?
No, I was gonna say that's also the center of mass, but it's not.
It doesn't matter.
Yeah.
This is the place that we've decided this thing's going to rotate about.
Okay.
When you're talking about torque, the R is the distance between where the torque is applied and where the thing rotates.
And because they're both applied to that same spot.
Exactly.
Okay.
That's why they're both 0.
That makes sense.
Yes. So the axis of rotation is right here. And since the axis of rotation is at the same, like there's no distance between those two, then
That makes
yeah.
sense.
Yeah.
So they're like on top, like just like if you think about it, it's like a tiny little point, and they're both there.
Yes.
Okay.
True statement. All right. Are we okay? Okay. Good conversation. All right. Now I'm going to mess with your heads a little bit because that's my job. Yay. You're welcome. So we know how to calculate moments of inertia. We understand this stuff. Now I've got a new question for you. 3 objects. A circular ring, something kind of like what we saw last time. A circular disc and a square loop have the same mass and the same outer dimension. The circular object has a diameter of 2r and the square loop has a side of 2r. The small circle at the center of each figure represents the axis of rotation. So to be very clear, I'm not going to roll these down a ramp because would we agree this one's not going to roll very easily? Okay, so that one would have a disadvantage. I'm putting an axis through the center and then I'm spinning it. Okay? The question says, or asks you, the task asks you, to rank the moment of inertia of those 3 objects. I'm going to give you 15 seconds to think, and then I'll give you some time to talk. So take a look at that and think. Let me see them. I'd like to see. I want to know how you did with this. It's a thinker of a situation. What does that first one say? That first part?
This means nothing.
Oh, okay. Okay, I like it. We got some thinking. I like it. Okay. So they all have the same mass, right?
Yeah.
They're all the same size, right? Should they all have the same moment of inertia?
No.
Okay. So no is the answer to that question because moment of inertia is about the mass, but it's also about the what?
Distribution of that.
Right, it's how it's distributed. Is the distribution of the mass the same in all of these cases? No. So far, so good. All right. Michael, talk me through something in your conversation.
Well, if moment of inertia, moment of inertia is just mass times the radius squared. So if masses are all the same, that doesn't matter. But
Okay.
So we're just look at the radius,
Mm-hmm.
and more like the center of mass is where that's at, sort of. So for C, comparing C to A, we have the same radius, but some mass is like on C, the corners are going to be outside, so they're going to be farther away than the farthest point on A is, I guess. So that's why we said C.
So like if there's a circle like this,
Yeah.
so that's like the circle that would be A.
So the mass in the corner is going to be farther away, so that means the moment of inertia on C is going to be greater. And then
Let me pause there and make sure. Does that make sense to people?
Mm-hmm.
Okay, so if I just want to recap what you just said, and then I'm going to let you keep talking. Is that fair? So C and A are similar, but if we look at some of the pieces, like this piece here and this piece here, they have the same situation right there, don't they? And there are some pieces up here, oops, come on, and down here that are the same as those guys. But what was your point there?
The corners of
Uh-huh.
C are farther away. Like, if you put C on top of A, the corners wouldn't fall on top of A. They'd fall outside of A.
Right, so like these little blue spots, if you take the little blue spots, these ones are going to be closer in, right, than these guys here. So the moment of inertia of C, you're saying, is bigger than A. Okay. So C is greater than A is an assertion that we're making.
And then,
You can go ahead, that's fine.
and then when we talked about between A and B,
Uh-huh.
A and B have the same mass, yet for A, all of it is on the outside, and for B, some of it's closer in. It's just like the thing we were watching roll on the ramp. B will have a smaller moment of inertia because some mass is closer, so the radius, like I don't know if you call it center mass, but like the average radius would be closer.
Right. So I'm just going to keep putting dots here. So there's a dot right there, and there is mass that's over here that's the same, right? But there's also mass that's really close in. So this dot, this little blob of mass, and this little blob of mass have different moments of inertia because this one's a lot closer in. So if you add up all of these little dots on this one and all of the corresponding little dots on this one, the radii here are all big, right? They're all R. And this one, some of them are R, but some of them are very, very close to 0. Is that okay? So this one's moment of inertia is actually much what? Much smaller. Much smaller. To actually figure out what the moment of inertia of those things are for each of them requires a little calculus. So if you're in calculus, if you've done integrals, that probably wouldn't surprise you, because just like we did in this problem, where we took these two masses and we added them together, right? We took the moment of inertia of this one and the moment of inertia of this one. You add them together, that's the total moment of inertia. We do the same thing for this. We just have to add up little tiny masses. Add up little tiny masses, add up little tiny masses, and by golly, this is what happens. Okay? As part of this class, we don't have to do any of those crazy derivations. They're really not that hard. If you want to see them, I can show them to you. But you do need to be familiar with the results of them. So I'm going to hand out to you a little sheet that's got some lists of moment of inertias. These got copied funny, but okay, you guys can handle it. I want you to hold on to this. You do not need to memorize these. It's not something that you will be tested over the facts of, but you do need to know how to use them. Okay? So I would recommend being familiar with it so that you're not shocked by the result, right? Like, oh my gosh. So just to take a look here at this, like at the very first one, you've got a slender rod rotating through the center. It just so happens when you do the integral, when you do the calculus, you add up all these pieces and all these pieces and keep moving in. It happens to be, and it's kind of weird, that it's 1/12, I don't know, 1/12 the total mass times the length of the rod squared. That's if you put the axis through the center. Take the same rod, move the axis to the end. Does it surprise you that the moment of inertia will change?
No.
It shouldn't, based on that very first example we did, right? Now it's only 1/3 ml, so it's a whole lot bigger here than it is here, which should make sense since we've got a whole lot more mass further out. Okay? Again, you do not have to have these memorized. You will need to know how to use them. So we'll practice that. Yeah.
Is capital M mass?
Capital M is the total mass, yep, of the object. Other ones that we will come to talk about a decent amount, things like this solid cylinder. So again, we're just adding up all of the mass throughout the cylinder. things, okay? So, again, you don't have to memorize this, but you do need to be familiar with it. Does that make sense to everybody? Okay.
We snuck some problems on the back too.
There are some problems on the back. We're not going to get to the problems today, although I would like you, why don't you read the first one and figure out which moment of inertia equation from the other side you're going to use. We'll work on these problems next time. Take a look at that first problem, though.